Okay, let's talk Introduction to Water Distribution. This is lecture 3. This will be a two-part lecture. I'll just kind of break this down where it's a little easier to view. And we're going to talk about water distribution systems. I'm essentially just going to scratch the surface. We are going to spend the majority of lecture 4, 5, 6, and 7, and 8 on pump design, but in this lecture here, lecture 3, I'm going to talk about the water distribution system sort of overall, the purpose, description, components, and some design considerations. And in the second part of the lecture, I'll get into the pipe flow equations, which you should already be well aware of from your fluid mechanics class that was a prerequisite to this course. All right, so the purpose of the water distribution systems is to move water from treatment plants to the homes. And included in that is where you're getting the raw water from. And so if you've got, an area here where, where you're getting your raw water source, be it a surface water source or a groundwater source, you've got to pump that raw water to your treatment plant, or if you've got a nice pristine water source, such as a really nice aquifer that you're pumping out of, that's fairly it meets water quality standards, you can pump it directly into your water distribution system. And so throughout the system, we have pumping to the treatment plant and then out into the water distribution system itself to get it to the end user, be it residential or commercial, government, or whatever. So the major components, the pumping stations, distribution storage, and distribution piping, and we're going to talk a little bit about that. As you look at this chart here, you can see that the pumping station, the distribution storage, and the distribution piping are the components of the system, and then you have subcomponents off of those components to further get into the details of how things are designed. And you can see here with the pumping station, you've got structural components, electrical components, the pumping itself, and then the piping. And then in the storage, you've got tanks and pipes and valves, and then again in the distribution piping, you've got pipes and valves. All right, so as you look at these subcomponents, as I've mentioned before, the pipe is the largest capital outlay that you're going to have in a water distribution system. You also have valves, which are used for a number of purposes. Pressure reducing, if you want to step the pressure down from a high pressure area to a low pressure area, or to lower the from high pressure to bring it down to a pressure that's more usable, and where you won't end up blowing residential piping apart. You've got pressure sustaining valves, which basically allow the pressure to be regulated at a particular pressure level. You've got check valves and shut-off valves, air relief and air vacuum, and then blow-off and drain valves at low points in the system. And then you've got the storage, which can be in the form of tower or a ground tank. We're actually going to take a field trip to one of the Raleigh Municipal Utility ground storage tanks. It's adjacent to one of their well houses, and we'll take a little tour of that. We've got pumps and then metering, which I've mentioned that it's important to meter, because otherwise, if you don't meter, people will have no incentive to conserve water. And then lastly, we've got fire hydrants you have to consider for fire flow. This is a pressure reducing valve, which has taps here that you measure pressure at various locations through the flow, and through mechanical means it can lower the valve, open and close the valve, particular to a certain degree, where it keeps the pressure at a particular, or drops the pressure down on the downflow side of that, where it can be used without, like I said before, blowing out the commercial or residential systems. There's a nice YouTube video here that you can view that explains further the pressure reducing valve. So if we've got a pressure reducing valve that's near this elevated tank, water tower here, you can see that you've got the line coming down that goes through that would be the main line going through the pressure reducing valve. you have isolation valves on both sides of that and a bypass, simply because there might be a need for repair of the pressure reducing valve and you need to take it offline, but you don't want to stop your flow going out into your main system. So thinking about pumps in the system and versus storage, the reason we have storage is that we don't want to, it'd be cost prohibitive to design and put a number of pumps in that would meet your peak flows and everything that we put at you, including fire flow. And so in addition, the pumps are also dependent upon electrical power. And so be it a backup system with generators or the main electrical grid, you can have problems with things going down, the pumps failing or whatever. But if you've got water and storage in these elevated storage tanks and water towers, then you essentially have a little bit of factor safety built in there. And with the storage, you also don't have to pump as much water during peak demands for such as emergency firefighting or peak demand during the particular time of day. So as we look at our major design considerations, we've got water demands based on the population served, and we break that out into residential, which are homes and apartments, commercial, that's retail, offices, hotels, restaurants, industrial, that's manufacturing and processing operations, and in some cases that can be the largest user in your system, because if you've got a manufacturing process that's heavily water dependent, you can see that would take could consume quite a bit of your daily loading for your water flow. And then we've got public water demands based on government facilities. And then on top of that, you've got fire flows needed to protect life and property. So if you get a major fire, you've got to be able to accommodate that needed fire flow to put water on the scene of the fire. And then you've got some critical conditions such as broken pipes. So we have to add in factor safety. The last thing that we need to be thinking about is the proximity of our water distribution service area to the source water. Are we going to have to pump this from miles and miles away to get it to the treatment plant and then out to the distribution system, or is the source very close, such as groundwater wells like we have in the city of Rolla? So if we look at a design flow rate that you'd have to have for your system and through your pipes and your pumps and for storage, etc., it'd be the water demand for a particular population plus fire flows plus a factor of safety for critical conditions. So we're going to have to figure out what our population you're going to serve is, and then what is the per capita use of the water times that population, and that's a particular method, and we'll talk about that in a second. Another method was just basically using per capita per day usage based on the type of industry and system that you have, and we can look at the American Water Works Association's work on looking at a number of water distribution systems across the United States to see what kind of use they have. There's also considerations we need to give for variation in population demand, and that can be daily or seasonally, and we've got the so-called peaking factors. We'll talk a little bit more about that. So as we look, and we have our daily per capita water demand times our population, that's our average daily demand. And so if we look at the first method, that would be by looking at average use across the United States by category. And so if you look at this, based on this work by Solly in 1998, you can see that for residential, we've got about 100 gallons per person per day that is used. That's on average across the number of systems that he sampled. And then the commercial use, again, that's industrial manufacturing. That's approximately 30 gallons per person per day. So if you've got a city of 10,000 people, you would assume that basically you're looking at about 300,000 gallons per day just associated with the commercial aspects of that wouldn't be used by the residential, but that's just a way to assess how much water you'd have to have for that commercial aspect. Industrial is 22 gallons, 17 gallons for public, and then you got to figure in some loss. There's going to be some leakages in the system, and so you have some loss. That's about 11 gallons per day, which is quite a bit. So total is about 180 gallons per person per day to take care of all the uses, and you'd multiply that by your population estimate. And you don't want to use the population that's currently in your service area today, but you want to look at the end of your design life. And so you need to estimate your population at the end of the design life. And so we'll talk a little bit more about that in a second. Method 2 is just looking at some American Waterworks Association studies where they looked at 392 water supply systems in the United States, and they see that they vary in terms of their range of what they're serving. You can see on the low end it's 190 to 370 liters per person per day, and on the upper end it's greater than 1140 liters per person per day. You can see that the majority, about a little over 64%, is in the neighborhood of between this 100 and 198 gallons. So that previous method that we had, where we had 180 gallons per person per day, is in the ballpark of what this particular independent research by the American Waterworks Association. So if you have a value for 180 to 200 gallons per day, that's fairly a good estimate for the majority of the water distribution systems that you'd be dealing with. So how do we estimate the population? And so we need to look at the population at the end of the design life. And as we look at that, we need to know what design life we're talking about, or design capacity. And so if we're looking at designing the river well field or the reservoir, you're looking at the outset of around 50 years for whatever that, the pertinences that would go with that, and designing a well field, the intakes and conduit to the treatment plant between 25 and 50 years. The pumps are basically around a 10-year design life, although you may get more longer service out of that, so much the better for your client. And then you've got the treatment plant, 10 to 15 years design period, a service reservoir, 20 to 25 years, and then the distribution system, the pipes and conduits, 25 to 50 years. So as you look and you're trying to estimate the population, so we know, okay, we're looking at a design life maybe 30 years down the road. What is our population? Here you can see the pure graphical extension method, where they've plotted the data from 1920 to 1990, and then they just extrapolate the population estimate. So in 1990 they were at 320,000 people. If you just did a straight line extension, that would come up to about 530,000 in this 30-year time span in this example in Chen's book. And so, that may or may not be a good method. You can actually, in some respects, I think most of the other methods that are out there would probably say this would be an overestimate, unless you're in that real growth period and it's just, an area that's being built out as a new growth area, and we'll talk about that in the next slide. So as you look, and as we look at population estimate models, part of this is looking at the way a particular urban area would grow, where you have this, rapid growth, which follows a geometric phase or an exponential phase, and then you get into this linear arithmetic growth phase, and then you get this declining growth phase as the urban, areas fill out and there's no more land to build on. And so this S-curve is a traditional way of estimating the population, and you can look at this. It's called a logistic curve. This is the equation for it, where you have to estimate some population saturation value. This is the PSAT. You've got this, the various things that go into this. If you wanted just to break them part of your, the various types, where you're, if you're in the young life of a particular area, let's say that it's a new community that gets started on the outskirts, or maybe a bedroom community of a major metropolitan area, then you might be in that geometric growth phase where you would estimate the full 30 years based on this exponential geometric growth. Or if you're in the declining area, again, that's a decay. This is the decay constant here in this equation. So as we look at, and I talked about in an earlier slide, you got variations of demand based on time of day. We also had the seasonality issue, and Branson, Missouri is a great example of that, where in the wintertime the population is much less than what you have in the summertime with all the tourists. Here is what you would have on a kind of a daily basis for most of your systems, where if you're in a typical winter day, You've got this peak demand here in the morning when everybody's getting ready to go to school or work or wherever to start their day. So they're taking showers and doing a number of other things, maybe some cooking and things like that. And then you have this lag in the middle of the day, and then you have this other peak that happens later on in the evening. Again, the people are coming home from work or coming home from school, and they're doing things that require water. And then you can see a maximum day for the year, and this might be during the summertime where you've got, a much more, maybe we're watering the yard in the morning and then we're watering it again, or more people are watering it again in the afternoon, and you get the bigger peaks. And so you can come up with a peaking factor based on whatever you have for your average, and then your peaking factor would be here in these range of demand factors that would help you figure out, okay, what's the peak flow that I'm going to have to design for. Fire demand, there's equations put out by the International Standards Organization, who basically sets the insurance rates, or they give an ISO rating for a particular town, which then will help set your homeowner's insurance, because a big part of that homeowner's cost is fire insurance. And so the International Standards Organization, or ISO, has this computational method, which is the NFF, or the needed fire flow at a location. And so it's a factor, or it's a flow rate based on a number of factors, including what's called a construction factor, an occupancy factor, an exposure factor, and a communication factor. And you can go through the ISO methodologies and pick out various values for the factors based on what the situation is, what type of construction you've got, what your occupancy is. This is a communication factor, and this is basically, how well do you have firewalls that isolate parts of the building where it won't just fire just spread through it rapidly. So you can go through those computations and look at the needed fire flow for various parts of your system. A commercial industrial area may have quite a bit higher, and likely will have quite a bit higher NFF, or the needed fire flow, than say a residential area would. If you have to design for the particular flow, then you're also going to have to know how long you're going to have to sustain that flow. And so American Water Works Association has put out this recommendation where based on your, we can use gallons per minute here, that's in liters per minute, and the minimum value you'd have for any water distribution system is to assume you've got about whatever it is, less than 9,000 liters per minute, but you're going to have to hold that for 2 hours. So whatever your design flow, your NFF at the particular location, you have to plan on holding that flow for a minimum of 2 hours for any system, and then it just goes up from there. If you've got an area of your system that say demands 30 to 34,000 liters per minute as a needed fire flow, then you're going to have to hold that for 7 hours. And so that goes along the lines of figuring out, what do I need in storage in my water tanks and ground, my water towers and my ground tanks for storage. That helps you figure out that volume of storage that you need. This is a schematic here of a water tower, and you can see that you've got a part of the tank is the operating range, so you would want to draw it down below this particular point right here, and then this is my emergency and fire range. So this would take care of, if you had power outages or you had leakage or a major bust somewhere, you get down into this emergency range of storage. Or if you have a big fire that's there for your storage, this is the area that you operate in on most of your water demand from your commercial, industrial, residential, government, public buildings. So if we look at pipe design considerations, we always have to figure out the minimum pipe that's needed to carry the flow that's required at the peak. And so we want to size that pipe based on that peak flow rate, and that's going to be the minimum diameter. And you're always going to spec up to a nominal available. So if you do some computations and say, okay, well, I compute that we need 5.5 inch diameter pipe, well, you're going to go to the next nominal size that's readily available from the manufacturer, which would, in this case would be a 6-inch pipe. And so you just bump it up. And then in terms of the type of pipe that you'd spec out, the material, that's going to be based on service conditions and for the most part. And also economics. But, the city of Rolla has been using ductile iron for a number of years, but they found that the soils are more corrosive around here. So as they replace things, they're going to a plastic pipe that's much more durable and will have a longer, longer life because it won't be corroded. And then the last thing to consider on your pipes is maximum allowable velocities. You don't want your velocity so high that you end up setting up a water hammer, hydraulic transients. And hydraulic transient, if you've ever been in a basically flushed a toilet or something where you have an instantaneous flow of water, you hear this clanging of the pipes. Well, that's water hammer. That's a hydraulic transient sets up. And if you basically have flow going in a particular pipe and all of a sudden you shut that down, then it goes, the energy goes from kinetic energy into a pressure energy, and so you get this water hammer, this water transient. And if you've got high velocities in your lines and you set up this water hammer, it can have tremendous damage, blow pipes out of the water. And this is an example from one in New York City where it's basically just exploded the pipe underground and you got a huge leak. And it's when you're converting that kinetic energy, that V squared over 2G, into pressure energy, P over gamma in the energy equation. And so it's got to go somewhere, and it basically goes, and becomes, the pressure builds up too much, or it just becomes very quickly, it's a transient thing, it becomes very quickly into pressure and really jacks it up really quickly, and you get this sometimes catastrophic events. All right, so if we look at pumps, we're going to talk a lot about pumps in the next several lectures, but just essentially the purpose is threefold here for the most part on our water distribution systems, where it's to maintain your service pressure, so it's like booster pumps, it's to refill your storage areas, and you might have fire service pumps that are designed into your system at different places to enhance the fire supply to those areas that would have high need. In terms of designing them, we're going to talk a lot about this pump performance curve or pump head curve that's supplied to you by the vendor. And the intersection of that and your system curve is something that you as the engineer, based on your system that you're designing for, you have to intersect, you have to build a system curve, and where these intersect is where the pump, for that particular pump, is going to, the flow rate's going to be. And we'll talk a lot about that in the coming lectures. And then you're going to have various operating conditions, various flow rates you're going to have to worry about. And so we'll talk a little bit about that as well in terms of, the range of flow conditions that you would have. All right, so that's going to conclude this particular lecture, the first part, and we'll go to part 2 here in just a second. You can view